So, for this it is common to use the editor that comes in the interface. So, we will write a script in Matlab, okay. I am going to start typing here. So, we are ready to start typing the little program. So, if you remember the communication system, bits are going to get generated, they are going to go through this BPSK mapper 0 to +1, 1 to -1, and then we are going to have noise getting added, and then the receiver does a thresholding at 0, right. So, that is the simple system, but to make theoretical plot, you just need to evaluate the Q function, right. So, you do not need anything more beyond that. So, let us say the first conversion is for rate and EB over N naught and all that. So, the way I usually like to write my code is to first define EB over N naught in dB, okay. So, this could be let us say 4 dB, okay, and then the rate, okay, the rate is 1, okay. So, how did I get these two things? EB over N naught could be anything else, you just have to fix that, you can change it to any other number, okay. The rate is 1 because I am doing uncoded BPSK, okay. So, this is 1 bit per symbol, okay. So, tomorrow if you do coding, we might change this parameter r, but for now r is 1, okay. So, once you do this, I know my formula for EB over N naught. EB over N naught is 1 by 2 r sigma squared. So, from that formula I can find what sigma should be. So, for that it is useful to first convert EB over N naught to from dB to actual value, okay. So, maybe I will write a quick little description here and then show you how that works, okay. So, EB over N naught is 1 by 2 r sigma squared. So, sigma is square root of 1 by 2 r times EB over N naught. Now, remember we are going to have EB over N naught in dB. So, EB over N naught is actually 10 power EB over N naught in dB divided by 10, right. So, if you have EB over N naught in dB, you divide it by 10 raised to the power 10, you will get EB over N naught, okay. So, you can plug that back in, okay. So, if you do that, you will get the value for sigma, okay. So, from EB over N naught in dB, right, so which is 4 or 5 or something, we can go to sigma. Sigma is the noise variance of the noise that you add, okay. So, this little formula one needs to do. You can do it in multiple ways, it is depending on your taste and how you like to program. So, maybe I will write like this, I will do an explicit conversion from EB over N naught to EB, 10 power EB N naught dB by 10, and then you can do sigma equals SQRT 1 by 2 by r by, if you do not like this, you can write 2 into r into EB N naught, okay. So, that gives you the value for sigma. So, this is most of the battle done, okay. So, all these are useful conversions, we should do that in the beginning. So, some sort of a setup for either the simulation or the theoretical plot that you might have, okay. So, now if you remember the value for bit error rate as a function of EB over N naught is given by this formula, right. It is just Q of square root of 2 times EB over N naught, right. So, once I have EB over N naught, I just have to plug it into this and get my value for bit error rate, but I know my Q is implemented as 0.5 ERFC of x by root 2. So, if I combine those two, I will get my value, okay. So, let me just write that down once again, okay. So, BER is Q of square root of 2 times EB over N naught, okay. And what is Q? Q is 0.5 ERFC of whatever is inside the argument of Q, you have to divide by root 2. So, this root 2 will cancel. So, you simply get EB over N naught, okay. So, this is a little formula that one might want to remember, and let us type that into my Matlab code, okay. I think that is the one, no, okay. Okay, I'm getting spun around here. There it is. Okay. So, how do I find bit error rate? Bit error rate theory. Okay, this is the theoretical formula is 0.5 times ERFC of SQRT of EB0. That is it. Okay. So, we can do a little display here, display EB0 dB and BERTH. Okay. So, this will just show you what the two values are, and let us try to run this. So, if you run it, you might have to save it. So, let us save it. I am going to save it into my folder that is available here. Let me make a little subfolder here. Maybe that is not easy to do, so I'll just leave it in this folder itself. Okay, so the title I'll give as here. I'll just call it BPSK sim. Okay, so that's just a file we have, and now we're ready to run it. And to run it, maybe we should run it from the command line. You can also run it from the thing, but let's run it from the command line. D colon, I forget the, oops, yeah, there it is. There it is. And you can check what is in the directory. Oh, I need to go into this 20 dot directory. Okay, so you can see my program BPSK sim .m. We can try to run it. Let's see if there are any errors. There are no errors, and as expected, if you remember 4 dB in the plot gave you around 10 power minus 2, and you can see that that is panning out here. 4 dB is 10 power minus 2. So, maybe we should check on the theoretical plot for let us say 6 dB. 6 dB is around 2 to 3. So, let us say 2.5 into 10 power minus 3, right. So, that is the plot. So, that's, let us see if that comes about in our BPSK sim. So, if I want 6 dB, I have to go back to my editor and change the EB over N0 to 6 dB, and then save it. You can come back to the command window and then run it again. You will get 2.4 into 10 power minus 3. So, that is it's close enough, and that is how I generated this plot. So, if you want to, for instance, get all these numbers together, you can make some simple modifications to the editor. You can make the EB and not DB as a vector, and maybe you might want to make some small changes here and there to make that work out, but this is a very basic piece of code to do that. Okay. So, now how do I verify the BER theoretical with the BER simulation? Okay. So, if you remember, I had mentioned you can write some simulation to actually transmit the messages, count the number of errors, and divide by the total number of bits sent to find the bit error rate. Let us do that next and then compare the two. Okay. So, for that I need to know how many bits I am going to send. Let me fix it at 10,000. Okay. So, it is some number you can play around with, you can change it if you like. And then first I will need the message vector. Okay. So, I will need to generate 10,000 bits of message, because it is a rate 1 uncoded BPSK. To generate random bits, the current code in Matlab is to use this command called rand_i. So, I am going to do that for the message. Rand_i 0. Okay, it's not 0, 1, comma 1, comma n. So, this will generate for me a string of random binary 0 and 1 values of length n, a vector of length n of this. So, I will illustrate this a little bit before I run it, but let me finish up my coding and then you can go back and see it. So, now I need to know, so this is number of bits of message, this is generate a random message, and the next thing I do, I have to do BPSK, right. So, I have to take my message to +1 and -1. Every time I have a 0 in the message, it should become +1, 1 should become -1. There is usually a little device that I use. So, let us call it S. S is 1 minus 2 into MSG. Okay, so, this is BPSK bit to symbol conversion. Okay. So, you can check what it does. If MSG is 0, I am going to get +1. If MSG is 1, I am going to get -1. Okay. So, this is a quick and dirty way to convert this BPSK modulation into a simple Matlab line of code. Okay. So, I have my symbol vector. Now, I need my received vector R. Okay. So, that is the transmission. The R is going to be S plus Gaussian noise with sigma as the standard deviation. So, Matlab has this little utility called rand_n, which will generate Gaussian distributed random variables, and how many of them do I want? N of them. Okay. So, this will generate n, rand_n generates unit variance distribution, values from that distribution. So, you multiply by sigma to get variance of sigma squared. Okay. So, this is R, and then now you can run your thresholding device. So, this is AWGN channel. And then now we have to do a thresholding, right. So, if R is greater than 0, I am going to say the transmitted message bit was transmitted symbol was +1, or the transmitted message bit was 0. Okay. And if R is less than 0, I am going to say the transmitted symbol was -1 and the transmitted message was 1. Okay. So, the way to again do this very easily, the message cap, which is M cap, which is what is decided on the other side, is to simply say R less than 0. Okay. So, this is the threshold. Okay. So, what will happen here is whenever R is negative, this condition is true. Okay. And true means 1 in as a number. If you want to compare it as a number, true means 1. Okay. And if R is positive, this condition is false, and false is 0. Okay. So, this quickly does a thresholding at 0 and gives you the bit that you want. Okay. So, I have a message and a message cap, and now I can compare message and message cap. Message is what I sent, message cap is what I have received. So, I can compare. And how do I compare? Comparing is not too bad. You can do it in multiple ways, but one can get a BER sim from the comparison. Okay. So, I am going to see if MSG is not equal to MSG cap. Okay. So, this will generate, wherever they are not equal, it will generate a 1, wherever it is equal, it will generate a 0. So, you can add it all up. This will give you the number of errors, and you divide by n, this will give you the error rate. Okay. So, whenever you do Monte Carlo simulations like this, it is good actually to have the number of errors separately stored. So, you might want to have that also. I will tell you why you need this. So, let us store that in one variable and then divide to get the error rate. Okay. And when you display, it is good to display BER sim and the number of errors and the n. Okay. So, in one shot you get a glimpse of what has happened, the EB over N naught in dB, the BER theoretical, the BER that you got from simulation, n errors and n. Okay. So, this is my little code. Let me save this. Okay. So, this does simulation and theory. What I am also going to do is show you some of these commands just to give you a sense of how they work. Okay. So, let us go to the Matlab command window, So, I showed you this code rand I. So, rand I, let me call it m, rand I of let us say 0 1 and then 1 comma. So, just for illustration we will use some 8. Okay. So, you can see it generated a random bit. If you run it again, it will generate another random bit, sequence of random bits. You can keep changing this, every iteration will be different, etc. So, this produces a random number generator. Okay. So, just it has a sequence like this. Okay. So, now once I do that, I can transmit my BPSK conversion work like that, right. So, you can see how this is working, 1 goes to -1, 0 goes to +1. Okay. And then we have the noise getting added. Maybe I should show you the noise separately. The normal, so this is normally distributed random variables, you can keep changing that, it will change. This is all variance 1. So, if you want to see sigma squared, so you have to multiply by sigma. Okay. So, this is noise like that. Okay. So, I wanted to get R is S plus this, okay, and this is R. Okay. And so, if you remember, I had this M cap, which is so you can see what has happened. Okay, just for comparison, maybe you need to see S and then this. Okay. So, you see -1 was transmitted, -0.92 is received, -1 was transmitted, -1.4 is received, -1 was transmitted, -1.4 was received, so on. Okay. So, that is the corresponding numbers that were received. So, now we had this M cap, which is R less than 0, and you can see that goes back to the bits. Okay. So, you can compare with M, you have the exact same M that was transmitted. Okay. So, this R less than 0 is a convenient device for BPSK. Is that okay? So, we did this for a very small case, and if you now I am going to run my BPSK sim. If you remember, that was for a SN EB over N naught of 6 dB, and then we are expecting 2.4 into 10 power minus 3 as the bit error rate. I was doing 10,000 bit simulation. Let us see what we get. Okay, sorry, I put some. Okay, so now the display is not that great. So, maybe we should do a format short G, which will make it a little bit better. And maybe we should get all of these guys in the same line. So, let us move this around. So, there you go. So, this is EB over N naught 6 dB. This is the theoretical bit error rate expected 2.3 into 10 power minus 3. Okay, it has so many accuracy, and then 0.003 is what I got in simulation. There were 30 errors out of 10,000. Okay, so you can see there is not an exact match, but close enough. But this kind of 30 is maybe not a very significant number. So what you can do if you want maybe better accuracy is to modify this n. You run for a larger number. Okay, so you run it for 100,000, let us say. Okay. This computer is quite powerful, and this program is very simple. It has enough memory. So 100,000 is not a big deal, but if you have a very small computer with not too much memory, then you might have to think about how much you can run it for, but you can usually run 100,000 very easily, and you can see the accuracy sort of improves. It comes closer to 0.2, and then you can do more simulations if you like. Some values will be closer. It's around 0.002. Okay. So now the reason why this number of times you repeat the thing is very important is, supposing I run it only 100 times. Okay. So what will happen is, if you run it only 100 times, this will keep giving you a number which you can't trust. Okay. So you see it gives you 0.01, sometimes it gives you 0. Okay. The 0 or 1 error while the prediction is 0.002. So that is why the number of errors you get in your simulation is very important. So typically when I run simulations, I like to simulate for as many blocks as needed, so that the number of errors is at least 100. Okay. So in your simulation, that is always a good number to keep in mind. If you do that, usually it is very good. So that is why if you make it 100,000, okay, or 1 lakh as we call it here, it usually is pretty good for this EB over N naught, okay, for the EB over N naught of 6. for the EB over N naught of 6. Okay. Now, if I change this EB over N naught to 10.5 for instance, okay, notice what happens, and if I run this, okay. So, 10.5 EB over N naught, I know my bit error rate is going to be around 10 power minus 6, and you can see the problem here, it goes to 0, right. 10 power minus 6 bit error rate, you are simulating only 10 power 5 and you are getting 0. So, what should you do? You should do something slightly smarter, and for that it is usually good not to keep increasing n. So, of course, you can keep increasing n to some 10 power something, but that is not very nice, because the reason is this is using storage of n. Okay. So, this works for small n, for large n this is not going to work very well. So, what you can do is you can make a loop. Okay. You can make a loop and have a cumulative n. So, what that is also a very nice thing to do. So, maybe you want to keep your n as 1000, okay, number of bits of message per block. Okay. So, you repeat the block multiple times. Okay. So, how many times do you want to repeat? For I equals 1 colon, let us say 100, okay, and then you have to end this somewhere here. Okay. It's still not ready to finish this. So, you repeat in blocks of 1000 100 times. Okay. So, this way your memory is not very high. Okay. Your memory, every time you create these vectors, you are only creating length 1000 vectors, but you are repeating it 100 times. So, you do not need too much memory, and you can still overall simulate for a very large number, but here it needs a little bit of careful work here. So, what you should do is you should have this n errors which is equal to 0 in the beginning, and you have to keep adding it up here. Is that okay? And finally, when you divide, so what I like to do usually is I also like to have a variable called n blocks, which is 100, and then I put n blocks here, okay, and then I divide by n, I further divide by n blocks to get my overall BER sim. So, this way my simulation will be a little slower because it is doing a loop, and loops are not that fast in Matlab, but I am not using so much storage, and I can increase my n blocks to as high a level as I like. Okay. So, for instance, I might make my n block as 10,000. Okay. So, now overall I will be simulating 10 power 8 bits, but I will be using only a memory of 1000 at a time. Okay. So, this will not be very slow, in at least in this computer. I believe this will run pretty fast. Let us and then if you look at it, I am counting my total errors, right. I am initially my number of errors is 0, and for every block I keep on adding the number of errors that I get. Finally, I divide by n, the number of bits in per block, and number of blocks also. So, overall this is a valid way to do my simulation. So, let us go and run this now. So, you see it took a little bit of time, but it was printing it as n. So, maybe I should change what I am printing here to n into n blocks, just to show you how many bits are being simulated. Let us go back and run it again. It was pretty fast, so it is not too bad these days. So, 1.08, still the number of errors is only 12. So, maybe you want to increase the block further. It was not too slow, so maybe we put one more 0 there. So, that way now we should get enough behavior. So, now you notice the delay, there is a little bit more of delay, but still finally you get the answer. It comes pretty good. 10 power minus 6 is the bit error rate you expect at 10.5 dB. You got 111 errors out of 10 power 8 transmissions. So, there was a lot of transmissions were needed to generate the errors, but you did get 111 errors, and you got a bit error rate simulation of 1.11 into 10 power minus 6. So, this is a basic setup in the BPSK simulation. Okay. So, now like I mentioned, we will keep this with us throughout. So, we will keep many elements in this thing of n blocks, and repeating over a block, generating a message, converting it into BPSK, sending it over, but except after the message is generated, we will put in our coding block here. Okay, where will the coding block come? Encoding will come here, and then before you do this threshold, you will not do the threshold, you will do a decoding here. Okay, we will introduce some code for encoding and decoding, and you can simulate error control code as well. And now you have to modify a lot of things, right. So, you have to modify rate here for coding, you have to modify all of that, and then we can see how this works. Okay. So, we will do this as we go along, but this is the simulation. So, what I am going to try and do is show you maybe a comparison on how easily will this same program run on Octave. So, let us try that. It is usually pretty good, but personally I use Matlab because we do have a license for Matlab. We have not had a reason to. So, I am going to open the file that we had. On Octave, it seems to have opened. So, let us not try the very ambitious version, we will try 6 dB and we will try number of blocks as 100, let us say. Okay. So, let me save this and let me here also I should go to that. Okay, it does not seem to like it. Okay. Okay. So, now we are on. So, let us run this BPSK sim here. Okay. So, it ran pretty fast. You saw that it gave you 244.00024. So, maybe we can also run 10.5. Then we needed 10 power 8, right. Okay. So, this will give you 10 power 8. So, let's save it, go to the command window and then run again. Takes a little bit of time. Okay, but it is managed to finish as well. You can see there were 116 errors this time, and then the bit error rate, theoretical and bit error rate practical, the simulation one agree in Octave as well. Okay. So, this is sort of true generally. You can write in Matlab and then the code more or less works with very little change in Octave as well. But remember, I was using just basic commands, I was not using any advanced package based Matlab commands. Usually you do not have to, these kind of commands are pretty good as well. Okay. So, that is the end of this lecture. Hopefully, you have learned enough from this. You will be expected to at least, so this code will be made available to you, you can take it and then you will be expected to run it, produce some results and then answer some assignments based on that. Okay. So, we will expect that you can do this. So, that is the end of this lecture. So, in the next lecture, I will start talking a little bit more about error control codes, how to build encoders for them, how to build decoders for them, and then we will have to write some code for doing encoding and decoding. We will do that after we learn about error control codes. Thank you very much.